Good morning, everyone. Welcome to our presentation at the International Symposium on Electromagnetic Theory. Unfortunately, a group of soldiers inside the Turkish army attempted a coup d'etat on July 15th, and more than 260 people died on that night, protecting the democratic Turkey. As a result of the failed attempt, a state of emergency has been declared for 3 months, and all academics are banned from traveling abroad. This affected our plans to visit Finland. We hope that the situation in Turkey will be stabilized sooner, and we will be glad to be with you at the upcoming URSI conferences. The title of our today's talk is Evolution of the Quadratic Functions of the Time Domain Waveguide Fields, and its aim is to attract the attention of the researchers to the evolutionary approach for the development of electrodynamics in time domain. Our goal is to derive the energetic field characteristics for the circular waveguide in the class of real-valued functions of time. To this aim, firstly, we have rearranged the Maxwell's equations in the same symmetry as Heaviside-Lorentz equations have, and later, modal bases, element of which depend on transverse coordinates, and modal amplitudes dependent on axial coordinates z and time t are derived. This gives us the possibility to exhibit the graphs for the power flow density, energy density, and velocity of transportation of the modal field energy evolution in time. The system of Maxwell's equations satisfying the boundary conditions over the waveguide surface are solved under needed initial conditions. We have modeled the problem for the waveguide with lossy medium. Sigma is the lossy parameter. Surfaces are perfect electric conductor. Cross-section of the waveguide S is regular along Z. A right-handed triplet of mutually orthogonal unit vectors is used where n is the outer normal to S, L is tangential to L, and Z is oriented along the axis OZ. A point of observation within the waveguide is specified by 3-component vector capital R, where the component small r varies within S. Z is a projection of R on OZ. T denotes observation time. My presentation is organized as shown on the slide. I will start with presenting our novel format of Maxwell's equation in SI units. Then derivation of the T and Tm time domain modal fields will be exhibited in terms of modal bases and modal amplitudes. And lastly, power flow density, energy density, and velocity of transportation of the modal field energy will be discussed as the quadratic functions of the waveguide modes. We start with standard Maxwell's equations in SI units, where E and H are the electric and magnetic field stand vectors with their dimensions of volt per meter and ampere per meter respectively. The free space constants mu naught and epsilon naught have been included in Maxwell's equations empirically. Sigma is a constant free parameter, and C is the numerical value of the speed of light in vacuum in SI units. We propose to introduce a pair of new empirical constants, mu naught ampere and epsilon naught volt, with the physical dimensions of ampere and volt respectively. Product of mu naught ampere and epsilon naught volt yields the speed of light in SI units. Scaling the field vectors from the Maxwell's equations results in a factorization of the dimensions volt per meter and up to ampere per meter of the original fields. So the new field vectors should have common dimensions of inverse matter. Substituting the field presentations yields Maxwell's equations in the same symmetry as Heaviside-Lorentz equations have. but Heaviside-Lorentz equations were originally derived in CGS units, whereas we have obtained this form in SI units. Significant merit of this form, in comparison with classical form, is presence of only one absolute constant, 1 over c, instead of those two empirical constants, mu naught and epsilon naught. In solving the time domain waveguide problems, equations should be supplemented with the boundary conditions over the waveguide contour L. And since partial differential equations belong to the hyperbolic type, problems should be supplemented with appropriate initial conditions when needed. As a particular case, we consider the waveguide with circular cross-section. The domain S is describable in polar coordinates. Position vector R and nublar transverse acts on space variables in the domain S of waveguide cross-section. The triple Z cross L equals N should be read as Z cross phi equals R. Definition of the basis settles solving Neumann and Dirichlet boundary eigenvalue problems for transverse Laplacian. Solving the problem by separation of variables yields psi and phi potentials. Every function from the set psi is specified by the size A of the circular contour L. We can use every function from the Neumann boundary eigenvalue problem set as a potential generating a basis E prime, H prime, and Z prime. And we can use every function from the Dirichlet boundary eigenvalue problem as a potential generating a basis for E double prime, H double prime, and Z double prime. We can write down the time domain field vectors T and Tm, which are generated by the elements of the basis, where the factors En, Bn, Hn, and En have the physical sense of the amplitudes of the field components. Substituting the Te field vectors to Maxwell's equations results in Klein-Gordon equation, where nu n squared is the eigenvalue in Neumann problem, and thereby that carry all the information about the contour L of the waveguide cross-section. Solution to this Klein-Gordon equation generates the modal amplitude of the longitudinal component of magnetic field, and H specifies the amplitudes of transverse field components. Substituting the Tm field vectors E double prime and H double prime to Maxwell's equation results in another Klein-Gordon equation. Solution to the Klein-Gordon equation generates the modal amplitude E of the electric field, and E specifies the amplitudes of the transverse field components. The Klein-Gordon equation is invariant under the relativistic Lorentz transformations. Taking into account this fact, Miller investigated the Klein-Gordon equation within the framework of group theory. He has discovered solving the Klein-Gordon equation via separation of the variables in various manners, dependently on a chosen orbit of symmetry. We consider now what the orbit 1 and 2 result in. Studies on Miller's orbit 1 results in the time harmonic solution. As opposed to the classical time harmonic field concept, where the complex valued exponential plays the conceptual role, we obtain the real valued solution for the T and Tm model amplitudes. The condition gamma n equals 0 and capital gamma n equals 0 yields the cutoff frequencies. Operations on Miller's orbit 2 yield the solutions to Klein-Gordon equation for the T and Tm model amplitudes. And the amplitudes of the transverse field components can be calculated by these formulas. For convenience of calculations, we replace t and z variables by their dimensionless equivalents. Calculation of the power flow density averaged over the waveguide cross-section, average value of the energy density in the same cross-section are presented here. Conservation of energy law is used to control of calculations. Velocity of transportation of the modal field energy through any fixed waveguide cross-section is specified as shown, and they all are presented graphically in the following slides. We start with the graphical results for the TE modes in a lossless waveguide with making usage of the separation of variables from Miller's orbit 1. Modal amplitude H of the longitudinal component of the magnetic field, amplitudes of transverse field components E and B are exhibited in the figure. Power flow density, average value of the energy density, velocity of transportation of the modal field energy can be seen from the second figure. It can be seen that the normalized velocity of the transportation of the modal field energy evolves in time. It can easily be observed that the magnitude of the velocity of the transport of energy cannot exceed the light velocity. Conservation of energy law and velocity of transportation of modal field energy are plotted in the third figure. We continue with the graphical results for the TE modes in a lossy waveguide with making usage of the separation of variables from Miller's orbit 1. It can be seen that the modal amplitudes are decaying in time. We continue with the graphical results for the TE modes in a lossless waveguide with making usage of the separation of variables from Miller's orbit 2. Operations on orbit 2 yields the Bessel functions. If A and B amplitudes have the same signs, direction of propagation of the modal waveform coincides with the direction of energy transportation. If A and B signs are opposite, modal waveform propagates along OZ axis. However, its power flow is transported in the opposite direction. A similar situation exists in a backward wave tube in microwave electronics. For the TE modes in a lossy waveguide, with making usage of the separation of variables from Miller's orbit 2, we again obtained the Bessel functions. In closing, I would like to attract the attention to the novel elements in our study. In the standard Maxwell's equation in SI units, the field vectors E and H have the physical dimensions of volt per meter and ampere per meter respectively. That's why the free space constants mu naught and epsilon naught have been installed therein empirically. We propose to introduce a pair of new constants where n is the force unit. Then the constants mu naught ampere and epsilon naught volt have the dimensions of ampere and volt respectively. So the field vectors can be scaled shown. Substitution of the scaled field vectors to the original Maxwell's equations rearranged them to the symmetrical form of Heaviside-Lorentz equations for the fields E and H, where the absolute constant 1 over c stands on the places of those mu naught and epsilon naught. Derivation of the quadratic field quantities as the real values functions of time need solving the waveguide problem in time domain directly. The solution is obtained herein within the framework of the evolutionary approach to electromagnetics, which was recognized recently as an alternative to the classical time harmonic field method. Klein-Gordon equation plays the central role in this approach. Miller discovered 10 orbits of symmetry of the Klein-Gordon equation. Herein we consider the solutions which correspond to product of exponentials, named orbit 1, and product of Bessel function and an exponential, namely orbit 2. One can find the solutions corresponding to the other orbits in our previous publications. In the appendix what follows, Miller's coordinate systems for separation of variables in Klein-Gordon equation are presented. This concludes our presentation. Thank you.